Consider the light coming out of a flashlight. Here's my flashlight. And it's one where you can adjust the zoom, and I'm going to adjust the zoom so that the light stays fairly narrow and goes nearly straight forward, creating a nice tight spot of light on the wall. Now this beam of light is full of a huge number of photons, all traveling individually like a wave to the right here. If I were to zoom in and just look at a few of those photons and just kind of draw their directional path like rays, okay, as they go towards the wall. The thing about normal light, like from a flashlight or a light bulb in a room, is that these photons, although they're coming from the same source, their phase is totally different one to the next. So for example, this one might have a phase that looks like this one might have a phase that looks like that, this one might have a phase that looks like that. Okay, they might all have the same wavelength. Okay, it's possible they could all have the same wavelength. But their phases are totally incoherent from each other, and we call that incoherent light. I can't predict anything about it. And because of that, trying to see their effect on each other is often difficult because they're all averaged out. You know, we can't get constructive interference or destructive interference very easily because we don't know how any photon is starting. Now, laser light is different. Laser light, the way you create a laser beam, so here's a laser, and I've got all these photons creating this laser beam. The way you create a laser beam is by causing one photon to stimulate another photon coming out in the exact phase. So if I were to draw these photons traveling like rays across the room, and if this one had a phase that looked like that, at this location in space, this one would have the exact phase, and this one have the same phase as well. So this is called coherent light, and meaning all the photons are in phase. Well, what that means is if I can somehow get these to interact with each other, I could accomplish interference. Like I know that at this location the phase is the same, and so I can have these add together or not, and depending on how I might change their paths. So coherent light is special. We can get it out of nature in certain circumstances, but generally it's created with lasers and other laboratory techniques. But the important thing about it is with this view, we can start to think about not just one photon at a time, but how all the photons are moving together. To do so, let me just draw a dotted line across this crest, and there's going to be another crest over here, and I'm going to draw a dotted line across that crest. And because they're all in phase, I get a plane, okay, or one line here that's perpendicular to the direction of travel. And I get one wavelength ahead, I get another plane. And so this can look like a line of crests, and one wavelength apart is another line of crests, and one wavelength apart from that is another line of crests. So I get these wavelengths between these, and I can show, okay, this is actually light traveling this way. The lines travel perpendicular to their length. And this would be a crest, that's a crest, this crest. Halfway in between would be a valley and another valley. So with this model, I can now describe the motion of this set of photons, or this wave, much like I would like a water wave, in the sense that when I see water waves coming in, I can usually see the full crest of a water wave that extends along the shore coming towards the shore. With this coherent light, this is the same idea, and I can do things like interference and other wave phenomenon as we've done with general waves. Now with this, again, I couldn't do that. If this was compared to a water wave, it would be like a bunch of just vibrational disturbances on the water surface. No one point is a crest. I can't really determine a crest near another crest because it's all randomized.